Hello and welcome to Performant Reflective Beauty. We'll be taking a deep dive into the hybrid ray-traced reflections used in Far Cry 6. I'll be speaking to the techniques we used and how they evolved to solve problems we encountered in the production. Ihor will give the inside view from behind the drivers of how to get the best performance of hardware-accelerated ray tracing. I'm Stephanie Brenham, the 3D team lead programmer on Far Cry 6, and I was deeply involved in driving performance and quality improvements needed to ship Far Cry 6. Previously, I worked on the Oscar award-winning software Maya and the Mental Ray for Maya integration. Mental Ray was a native ray tracing renderer, pivotal in bringing ray tracing to film and VFX, and was used in such movies as Matrix Reloaded and Matrix Revolutions. You could say that by presenting this talk on ray tracing in games, it means that for me, everything old is new again. I'm presenting on behalf of Anton Remenzenko, the senior rendering programmer responsible for this feature. Unfortunately, Anton was not able to make this presentation. However, I hope to do justice to his tremendous work in his place. Also key to hybrid ray-traced reflections are Alexei Shevchenko and Mikhail Shostak. We wouldn't have this presentation today without them. Far Cry 6 is a first-person shooter situated in a fictional island, Yara. It's a humid, tropical setting supported by a brand new, fully dynamic weather system. The frequent rain, like the rain outside you might hear, and storms present the player with a lot of wet, slick, and highly reflective surfaces. Ray tracing was key for adding the extra realism and immersion for our PC players. Note, for full details on the weather system, please see the excellent talk simulating tropical weather in Far Cry 6 done by my team members and presented here at GDC 2022. The fictional island Yara, where Far Cry 6 takes place, has been suffering from decades of economic sanctions. People have no choice but to keep their old cars running. It makes for a game world filled with beautiful, old, shiny cars that have prominent chrome features. Hardware ray tracing provides the off-screen reflections that really help deliver that classic look so key to our vehicles. In Far Cry 6, we begin by generating rays that will be used for all of our different types of reflection traces. The next is the SSLR pass, and this determines where hardware-accelerated ray tracing is required. I'd like to note that our screen space reflections are based on the methodologies presented in Stochastic Screen Space Reflections, a SIGGRAPH 2015 talk. The next pass is our hardware-accelerated ray tracing and lighting that excludes particles. Particles are a special case, and that is best handled in a separate second hardware ray tracing pass. In our final pass, we integrate the results from all the different types of our reflections. In Far Cry 6, we use a GGX BRDF to determine the reflection lobe. Complete coverage of the reflection lobe using ray tracing is prohibitively expensive performance-wise. Instead, we use importance sampling to determine more optimal ray placement. Importance sampling is then combined with a pre-generated Hammersley sequence to ensure even distribution. However, we'll need to use these rays for several different passes, so we store the rays in a buffer for later use. Which means even with importance sampling, we still had too many rays per texel. We wanted one ray per texel per frame. But a single ray does not provide enough information to calculate the reflection correctly, except for the case of a perfect mirror. Luckily, all close neighboring pixels use similar importance sampling and the same Hammersley distribution. Because of this, we're able to collect the hit points from the neighbor's ray and reuse these values in the BRDF integration. Our investigations into ray placement show that the values from the rays in the boundary of the hemisphere almost never contribute significantly to the BRDF integration. To make use of our rays, the best use of our rays, we shrink the hemisphere by reshooting rays when needed and only using the values from the more significant portion of the hemisphere. We store our rays in a half-resolution buffer that is upscaled with temporal accumulation. The resulting ray buffer is used for all of our different types of reflection traces. Our first reflection trace is in screen space. The screen space trace is much faster than the hardware-accelerated ray trace in world space. Our SSLR is a fallback for when the results from the hardware ray tracing are unavailable. The green in this image represents where we would use screen space reflections exclusively. But the SSLR that we used in Far Cry 5 proved to be unstable with its limited trace steps. The problem was that our hierarchical Z trace could run out of iterations, and with slow camera rotation, flickering would appear as gaps formed and disappeared in the reflections. Our solution was to switch to a linear trace done in MIP0 of our depth buffer hierarchy. We initially take 64 evenly spaced steps to roughly check for intersections. At each point, we check if we have landed behind the min depth stored for that pixel. When we land behind geometry, we go over the last step with 8 evenly spaced steps looking for the point of intersection. This linear trace produces stable results even when the camera is rotating, and it has the same performance as the hierarchical Z trace. Yay! But we found that edges were sometimes being missed. Edges were missed because the rough linear steps could pass over edges of geometry. Both of these points of the linear trace are unobscured and not behind geometry in the depth buffer. Subsequently, the linear trace will simply step over the edge and continue. To address the problem of missing edges, we added random ray start offsets. With this, edges became much more stable, which is exactly what we were hoping for, except we knew that glossy reflections don't need a trace with such a high level of accuracy. We wanted something more performant for glossy reflections. We needed to find a way to identify where our use of linear trace and where we need to use our linear trace and where reflections could be less precise. To do this, we classify tiles to determine the level of precision they require for our screen space reflections. For materials with high smoothness, like puddles or chrome, we need to use the high precision trace, but the other reflective surfaces can be done with a more performant trace. You see in this image, much of the reflective surfaces are colored green to show a fast trace was done. The high precision trace is reserved for the mirror-like surfaces of the puddles. For glossy reflections, we use a cone trace. The cone angle is increased for rougher materials, giving us even more ability to dynamically tune the performance. The first circle is chosen to have an area of approximately a pixel, which maps to MIP0. At each step in the iteration, the screen space of the circle is mapped to the closest power of 2, and then the corresponding MIP level of the depth map is sampled. While the precision of the cone trace is low, our investigations showed that the rough surfaces got a quality boost by adding these reflections. We had achieved our goal, performant glossy reflections. Yes! We begin looking at the hardware-accelerated ray tracing in Far Cry 6. Even with all the hardware advancements, the cost of tracing rays in world space is still tremendously high. Certain industry standards have emerged to help. On the left side is a typical scene in Far Cry 6. On the right side, this space is divided up using a bounding volume hierarchy, a BVH. For traversing BVH trees, the structure is generally divided into a top-level acceleration structure, or TLAS, and a bottom-level acceleration structure, BLAS. Ihor will go into more details about the BVH tree and performance tips. In this image, the teal and blue reflections show where we have started to add ray tracing. For performance reasons, we are selective about where we use hardware ray tracing. Our BVH is limited in the distance it covers, and later Ihor will go into why this is key for optimal performance. But what this means for us right now is that the far distance reflections are computed with screen space traces exclusively. On the other hand, for distances close to the player, we know that SSLR is unlikely to be realistic because so much of the reflection will come from things that are off-screen. Hence, we use hardware ray tracing for all close distance reflections. But the mid-distances, well, that depends on our confidence. When reading from the depth buffer, changes between neighboring pixels are normally small, as shown with these two arrows. But when there is a sudden and large difference in depth, like with this third arrow, it indicates missing off-screen details. In these places, we have a low confidence in the screen space trace. We also track the confidence level with hardware ray tracing. Close to the player, we have 100% confidence in the hardware ray-traced reflections. As the reflections get closer to the outer edge of the BVH, the confidence level is gradually decreased to 0. This prevents popping. We now come back to this image. The green reflections are where we have full confidence in SSLR and use it exclusively. The teal is where we have our hybrid reflections. We compare the confidence scores and use the trace with the highest confidence. The darker blue is where we have no confidence in the screen space trace and we exclusively use hardware ray-traced reflections. And those other reflections? That's where we have no confidence in either the screen space trace nor the hardware ray trace, and we make use of environment map reflections. Please see the excellent talk simulating tropical in Far Cry 6 for more details on environment maps. My colleagues have done an excellent job. Up until now, we've made really good use of the mental model I introduced at the beginning that shows creating reflections as a linear process. This mental model is useful to focus our limited time on the algorithms directly related to implementing reflections. But of course, this model hides all the interactions between the different pipelines. So for just a minute, let's peek behind the curtain to see some more details. There's a lot of details on this graph, and you might not be able to read it all at this moment. But when you have a chance to see the slides or video of this presentation, this graph will be very useful to help you understand how everything fits together. For now, the key details are build AS, or build acceleration structure, is done on async compute, but this only happens when we are GPU bound, usually around 2K and up. Otherwise, build acceleration structure stays on the GPU pipeline. Also note that particles have their own acceleration structure, and it builds in under 0.1 millisecond normally. Building the acceleration structure on async compute would be slower because of the synchronization overhead. Speaking of acceleration structure, in our BVH tree, we adhere to the principle of 1 blast per object, or material. But per object is preferred. Per material should be avoided, particularly when it leads to a blast with a lot of empty space between submeshes. Building and rebuilding the acceleration structure is performance intensive. Static blasts are built only once, but skinned blasts need to be constantly updated, so an endless loop is formed to update these blasts from oldest to newest. First-person player character, weapon, and attachments are all rebuilt every frame. To keep performance reasonable, we build only 16 blasts per frame. This can be a mix of static and/or skinned. Now we come back to the original mental model and we are on the hardware ray tracing step. By design, we do not have separate lighting shaders for each material. Instead, our lighting is done immediately after the trace in the same shader. Later, Ihor will also dive into ray tracing shader tables and the performance impact they have. To support the mixed trace and lighting shader, we created unified lighting parameters that are stored per vertex. Each material requires a specialized shader to map its lighting to the unified lighting parameters. The object materials are parsed in the blast creation stage. This moves the performance hit of shader variations from the per frame lighting work to the one-time process of blast creation. Calculating lighting is different when using hardware ray tracing than in the traditional graphics pipeline. In the graphics pipeline, the rasterizer provides the interpolated values to the pixel shaders to facilitate lighting. However, in the ray tracing pipeline, the interpolation is done directly in the lighting shader. That's because the lighting shader operates on primitives, not pixels. For this reason, our unified lighting parameters are stored in the DXR primitives for access by the lighting shader. To populate the primitive data, we unwrap the vertex and index buffers before the blast is created. This causes duplication within the DXR primitive, but it means that the primitive vertices follow each other in VRRAM. This ensures better coherency for interpolation. As well, the index buffer is not needed for lighting computations. This removes an additional indirection. The vertex data is packed to minimize impact on VRAM. Our primitive buffer holds all the primitive information from every blast in our game. It has a set size of 192 megabytes. We also have a primitive offset buffer. The DXR API provides a primitive index to identify primitives for blast instances. The offset buffer maps the primitive index to the correct data in the primitive buffer. We have a fixed number of geometries per blast. Based on the data we have in our game, a maximum of 32 geometries per blast works well. In comparison with some other implementations, overall, this structure gives us the performance benefit of only one indirection through the primitive offset buffer. In order to light our primitives, we interpolate the primitive vertices using barycentric coordinates. Then, using this information, we calculate the interpolated values for our unified lighting parameters. Other factors that contribute to lighting the primitive are the sun, global illumination, environment maps, and as well, shadows. Possible future work would be to add support for dynamic lights. Here you see the barycentric coordinates of the hardware ray tracing primitives in the reflection. With this and the unified lighting parameters, we have all that we need to interpolate the lighting data across the primitives in the reflection. This image shows the resulting primitive lighting in the reflection. Without texture sampling, areas with less geometric detail can appear plain. However, objects with rich geometric details play to the strengths of our implementation. Far Cry games are known for their explosions and dynamic systemic fire. In addition, new to Far Cry 6 is Poison, which is featured heavily in gameplay. As seen here, Poison's distinctive red color also features prominently in reflections. Particle reflections are important for the visual quality of Far Cry 6. But of course, the complication is that particles are just 2D billboards. To trace reflections of particles, we begin by reusing the ray length as it was determined in the previous traces. This allows us to clip invisible particles like the red sprite, which is hidden from the block, or by the block. Using the predetermined ray length and one blast instance per particle, we collect all particles along the ray to allow us to blend properly. Performance tip. A separate TLAS for particles gives a performance boost when traversing the particle acceleration structure to trace rays. Now on the previous slide, the reflection ray was conveniently intersected with all the particle boards in the diagram. It's so convenient, it's as if someone had designed it that way. However, particle sprites are oriented to face the camera, not the reflection ray. This means that often the reflection ray will not intersect with the particle boards, as seen with this blue sprite. To solve this, we have added extra quads that lay in the planes of the local coordinate system for each particle. Using these extra quads, the reflections ray will intersect with the green quad. But it is a performance drain to check for intersections on all the extra quads, just in case. Our solution was to sort all the quads and mask them in the BVH tree based on the view space axis directions. This allows us to ignore the blue and red quads. A further optimization is we use a simplified lighting model for particle reflections. In this comparison, we're looking at the two types of particle reflections found in our game. The red outline draws your attention to the reflection in the puddles in the bottom portion of both images. The left is the screen space reflections, and the right is the hardware ray traced reflections. You can see what a quality improvement the particle hardware ray tracing adds throughout our game world, whether it be for poison clouds or fiery explosions. This last pass is integration. Here we take the results from neighboring pixels and weight them by the BRDF coefficient. For performance reasons, this integration is split across 2 frames. On screen, you can see our pattern for collecting data from neighboring pixels as decided per frame. We process the rays from 9 neighbors per frame. We weight the central pixel, so it's always included since it's required for the ideal mirror reflections. After integration, we use temporal accumulation so that in total, we use data from 17 neighbors. Temporal accumulation requires reflection motion data. Most reflection motion is calculated using reprojection. Let's start with this typical reflection. First, the reflection is reprojected through the surface plane into a world space position. Then the world space position of the reprojection is reconstructed in screen space using the previous frame's camera. With the 2 points in screen space, we take the difference to determine the reflection motion vector. Note, reprojection completely breaks for objects that move with the camera, like first-person player character and player-driven vehicles. For these cases, we use G-buffer motion. With the reflection motion, we can now do temporal accumulation. Unlike TAA, reflection history is not rejected based on motion vector length. In fact, ignoring large reflection motion vectors can result in specular explosions on rough surfaces. Instead, we need to validate the reflection history using the motion derivative. We discard incoherent reflection motion. This image was created without hardware ray tracing. Some details in this reflection immediately catch my eye. Underneath the truck, it's unnaturally bright. It's like the truck is floating. It's the classic Peter Pan problem. As well, the building partially disappears in the reflection, and it looks very wrong. This is the same image, but with a mask layered on to show where we use screen space reflections, hybrid reflections, and hardware ray traced reflections. We can immediately see that hardware ray tracing will fill in details in the areas we noted. But we can also see that without hardware ray tracing, the image will be missing out on at least 2 additional sources of reflection details. Now, when you add everything together, both screen space reflections and hardware accelerated ray tracing, into a hybrid result, you get a rather pleasing image. I would go so far as to say it's a picture of performant reflective beauty. Thank you all so much. I'd like to hand this over to Ihor to give you the inside scoop on getting the best performance out of your hardware accelerated ray tracing.
Hey everyone, my name is Ihor, and I'll be covering the performance side of Hybrid Raytraced Reflections in Far Cry 6. From the AMD team, we had both Zhu and I as GPU dev techs for Far Cry 6, and we had John Hartwig as a CPU dev tech for Far Cry 6. I'll be going over various techniques we use to optimize the Hybrid Raytraced Reflections. Mainly, I'll be looking at shader table management, hit shader design, and BVH building. All of the performance captures in this presentation were done on a Radeon 6800 XT GPU with a Ryzen 3970X Threadripper. Before we go over optimizations, I'll be giving a quick overview of the Radeon GPU Profiler UI, or RGP for short. Here's a pretty typical RGP trace you might see if you take a capture of your application. The top window is the wavefront occupancy window, which shows how much of the GPU is filled with work at any point in time. You can see that the different waves executing are color-coded, so yellow corresponds to compute shader workloads, green corresponds to vertex shader workloads, and blue corresponds to pixel shader workloads. And the highlighted blue area are waves executing on the graphics queue, while the highlighted yellow area are waves executing on the async compute queue. Below that, we have high-frequency counters, which show us our cache hit rates for the various caches on our GPUs. And below that, we have the event timeline window, which shows us the different draws and dispatches and barriers that are being issued. And we can select different events here and look at them in the event details window, where we can see how long they took to execute, and if it's a draw or dispatch, we can see its max theoretical occupancy, as well as total wavefronts that it actually spawned. Here's what a RGP trace looks like for Far Cry 6's Hybrid Raytraced Reflections. You can see that I highlighted various parts of the frame that are executing here, but the ones that we're going to be looking at are the BVH building on the left and DXR ray tracing on the right, both of which have red waves. So ray tracing is a latency-heavy operation, and is very affected by divergence. We're going to be looking at three forms of divergence and how Far Cry 6 tackles them, and they are ray divergence, shader table divergence, and resource divergence. So ray divergence is when different rays have to take different amounts of traversals to actually find an intersection within the same wave. This can happen if you have different rays that hit different objects in your scene, or if some rays happen to hit a more detailed part of a BLAS that requires more traversals than surrounding areas. You can see this shown in this diagram here, where we have three different rays that hit three different boxes. Each box has a number which signifies how many traversals that ray will have to go through to find the intersection in that box. And then on the right, we see how this actually executes in our wave. So each thread corresponds to a ray, and as our wave traverses, certain threads happen to find intersections quicker than others. But because the wave is a SIMD unit that has to be synchronized in its program execution, even though some threads have already finished executing or have found an intersection, they still get stalled until the worst case thread finds its intersection, meaning that we have to wait in this example until we go through 4 traversals until we can start processing our intersection and doing something with it. The next form of divergence is shader table divergence, which occurs when different rays have to evaluate different shader table entries, usually for hit and miss shaders. This sometimes happens if you have different materials that have different hit shaders. And we show that here in our diagram, where we have 3 different rays that hit 3 different boxes again. Each box is color-coded to represent a different material, and that material has its own hit shader. On the right, we see how this actually executes. And the mental model is that it executes like a series of branches. So what happens is we first do if threads are green material, then execute the green hit shader. And then we do if threads are teal material, then do the teal hit shader, and so on until we go through all of the unique hit shaders within our wave, which is a very serial operation and can get very slow. If instead we have all of our threads have the same hit shader, then they all execute that same hit shader all at once. and then we can move on to doing other workloads on that wave. The last form of divergence is resource divergence, which occurs when a shader issues a resource read, but different threads in the wave are trying to access different descriptors. So from a hardware point of view, when we issue a buffer read or a texture sample, the hardware uses an SGPR to determine the descriptors, meaning that it assumes that the resource we are actually reading are uniform across the whole wave. The problem is, if you look at our left example, if we have different threads trying to read from different textures in a texture descriptor array, maybe we're doing a texture array.sample like we have in our middle line of code. What the hardware has to do is it needs to loop through all of the unique resources in our wave and have each issue the read for the threads that are using that resource. In HLSL, this is done when we write non-uniform resource index. And the way this actually executes can be seen in the middle, where we do read texture A for all of the threads that happen to require that texture. And then we issue read texture B for all of the threads that need to read that texture. And then for texture D and all of the other textures that need to be read within our wave. And this can get very slow again because it's very serial. If instead we were able to rewrite our code so that we only ever read one texture, then we just read that texture from all of our threads, and then we can continue with our other instructions right after. So over here, we're going to be looking at what we want from the assembly when we write our ray tracing shaders. So you can see the pseudocode on the left, which shows how the actual hit shader execution happens. And so what it does is we first do if ray intersects, and all of the rays that pass that then calculate their hit table index, which does not have to be uniform for a thread group. And then we do a switch on this hit table index, with each case being another shader table entry. From an assembly standpoint, we want these shader table entry function calls to get inlined. And if they happen to share some common code paths, then we want the shader compiler to group those together as an optimization. The problem comes if we have a very large shader table. We can run into a case where we have too many shaders to inline. And instead what the compiler will do is it will emulate a function calling convention on the GPU, with loading and storing function arguments and return values done in LDS. To figure out if you're actually running into this issue that your shader table isn't inlined, you can take an RGP capture and then highlight your event. And if you see a tab that says shader table, then you know that your shader tables are not inlined. And you can see a picture of what this looks like at the bottom, where we have all of the shader table entries names, and then we have a graph showing the actual execution flow for the different ray tracing shaders. If you click on the ISA, you'll have different ISA for the different shader table entries. And if you look at it, you'll notice that there's a lot of excess instructions that need to be executed, as well as extra LDS traffic. And all of this is just mimicking a function calling convention. It's not executing the code that we have in our HLSL, it's just pipelining things together. And it's a lot of extra work. So on a Radeon 6800 XT at 4K, forcing the shader table to not be in line for Far Cry 6 makes everything run about 2 to 3 times slower than it would otherwise for the actual ray tracing operation. So looking at what Far Cry 6 does, as Stephanie mentioned, we have a single hit shader, which interpolates vertex attributes to store all of our material properties, and we have a single miss shader, which is just empty. There's no code there. Because we have such a small shader table, all of our shader table entries get inlined. So even though our miss shader is an entry, because it's empty, it doesn't actually add anything to the assembly. It gets completely optimized out. We avoid shader table divergence because we only ever have one hit shader. And again, because the miss shader is empty, even if we run into a case where some threads miss and some threads hit, we only ever pay the cost for the hit because the miss is empty, so there's no extra latency that gets added for it. We avoid resource divergence because all of our DXR primitives are stored in global buffers. We don't try to load for different rays, different resources. Instead, what we do is we calculate different offsets based off of the geometry we happen to hit, but we're only ever issuing buffer reads to the same resources for all threads. And for ray divergence, we partially mitigate it during the BVH building process, but we'll get into that in the next section. You can see the code here for the actual hit shader, where we calculate our offsets, we get our DXR primitive, we do the barycentric interpolation of the material properties, and then we calculate the lighting and put it in our payload. We have a list of AMD Raytracing performance recommendations on GPUOpen that you can check out at the slide link over here. And these will include some of the things I've already said, as well as others that I haven't gone through. Now we'll be going over the BVH workloads and how we optimize them. Before we actually get into BVH building, we first need to generate vertices for them. And because we have animated objects, you do have to stream out vertices generally with animations applied every frame. So Far Cry 6 chose to use a compute shader to generate these vertices instead of a vertex or geometry or tessellation related shaders. And there's a couple of benefits to doing it this way. If you wanted to use the geometry related shaders and just write out add a UAV right at the end of them, and then use this in your already existing geometry passes, you will have to disable vertex and object culling because you don't want to just limit your BVHs to screen space information. You want to have world information. But if you do that, your geometry passes then get a lot slower. And so with a compute shader, you avoid all of this by just doing it in a compute shader, whereas your geometry passes remain untouched. We also avoid redundancy with vertex cache misses. So what can happen is if you, for example, just have your vertex shaders write a UAV, different waves can sometimes miss the vertex cache. And so those different waves, those different threads can sometimes write to the same vertex redundantly. If you instead have a compute shader, then you get the guarantee that every thread is going to write to every DXR primitive once. There's going to be a one-to-one relationship there. You're not going to get any redundancy. There's also some potential for reuse of this data that we're generating. You can potentially reuse these positions that we're streaming out for shadow passes and avoid reanimating them for those passes. But this wasn't something that we had the time to actually try out on Far Cry 6. So this is more of a future thing to experiment with. So again, if we pull up our RGP trace, you'll notice that the BVH building happens on the async compute queue. And there was a lot of benefits to doing this. BVH building can be very low occupancy and very good to overlap with because of that. It has very high latency, so we don't want to stall other workloads that are happening. And you can see over here what the BVH building would look like if it was on the graphics queue. And there's just not a lot of waves that are being generated, especially during TLAS building. And so even though the BVH building uses a lot of memory traffic, there's still a lot of ALU hardware that's idle during this time, which makes it a good candidate for overlap. And because nothing else in the frame outside of the ray tracing actually requires the BVH data, you can overlap with a lot of workloads like gbuffers or shadows or any other early frame workloads. For Far Cry 6, we found that doing this actually gave us about 0.4 to 0.8 milliseconds of a speed up on average compared to doing it on the graphics queue. One of the things that we didn't have a chance to do was move the actual vertex generation for BVHs on the async compute queue. And this was because the complexity was a lot harder. You would have to issue cross-queue barriers to make sure that your vertex and index buffers that you're going to be using are correctly synchronized. And so this is maybe something to try out for future titles and see how much of a performance gain is to be had here. So over here you can see how we actually populate our command lists and what that looks like. We have one compute command list with all of our build BVH calls and one compute queue submission with one synchronization with the actual graphics queue for ray tracing. And this is very good to do because on PC, synchronizations between queues are more expensive than they are in console. So you do want to limit them where you can to save on performance. And over here we have just about the simplest form of synchronization that you can ask for BVH building, which makes it very easy to integrate from that standpoint. So one thing to keep in mind is that there can be a lot of variance between BVH build times in different frames, depending on what sort of assets you're actually sending to be built. And over here we have 3 different RGP traces, and you can see that they can take drastically different amounts of time to actually execute, over a millisecond of a difference. And so to account for this, you want to make sure that you issue your compute queue submission early enough in the frame that you can account for this variance, because you don't want to run into a situation where all of your graphics queue work has finished, but your async compute queue hasn't. And so you don't have any more work that overlaps, and then you just kind of run it synchronously as if it wasn't on async compute. But there is a benefit here also to having this on async compute, which is that if it was on graphics, we would have a lot higher of a variance between frames, but because it's all overlapped on async compute queue, we hide a lot of that variance from our frame times. And so it makes our frame rate much more stable than it otherwise would be, which is a very good property to have from doing it this way. Over here we have a picture of Far Cry 6 BVH being ray traced and the various traversal counters. If you look at where the black arrow is actually pointing, you'll notice that even though a ray doesn't intersect anything, it still has to traverse the tree to confirm that it does not intersect any geometry, which takes time. And so if you happen to have a very dense TLAS, then it will take a lot more traversal from these rays to actually confirm that they miss. And this is a big reason why limiting your TLAS is a big net win, and it was for our particles, where we only had particles in the TLAS instead of other geometry. It made the traversals much faster. A thing to keep in mind is that the camera is usually deep in your TLAS tree. You're going to be close to the geometry, you're going to be close to a lot of the things in your world, you're not going to be in the bird's eye view. And so if you have a deep TLAS, you're going to be paying that traversal in the common case for most of your rays. And so you really want to avoid putting a lot of objects in your TLAS if that's possible. One thing to also draw your attention to is the ray divergence box in the image. So over here is actually a perfect example of what ray divergence would look like. You have a bunch of rays there that are red, which would take a lot longer to traverse, but they're very close to different rays that are much brighter. And so if those rays get grouped together in a single wave, then you're going to be running into the ray divergence issues that I mentioned before. So how does Far Cry 6 deal with these issues? Well, for the TLAS issue, we limit our TLAS to only include objects that are within the 100 unit radius from the camera. And you can see in this picture what that actually looks like. The TLAS only ever goes so far. Most of the world is not in it. We do have the terrain that actually extends much farther, but the terrain is clip mapped, so it ends up progressively lowering its resolution. For the BLAS objects, we put them into our BVHs at a lower LOD, meaning that we don't use ever the full LOD. We use a capped lower LOD for all of our BLASs. And this helps a lot with ray divergence because it makes our worst case a lot better. We just have shallower trees to traverse, and so in the worst case, we won't have to go as deep into a tree to find an intersection. But this is also something that you generally might want to do to some degree for reflections. You don't always need the most detailed reflections, and for distant objects, you 100% want lower LODs because you want to filter your geometry. One of the benefits here is that because we're doing reflections, having lower detailed objects in our reflections doesn't really cause any major visual artifacts. It still generally looks good. So just to conclude our BVH and BLAS tips for hybrid reflections, it's worth considering using a compute shader for vertex generation. In Far Cry 6, our BLAS positions and DXR primitive attributes are all exported in a single compute shader dispatch. We recommend trying async compute queue for your BLAS and TLAS building. BLAS can be higher occupancy, but TLAS is generally low occupancy, and so it was a good performance win for us. You want to try to limit the geometry that's in your TLAS just to avoid the cost of traversals. And for reflections specifically, consider having lower LODs for your BLASs. It will give you faster tracing and lower VRAM usage, and as mentioned before, it generally still looks good. So we're now going to be talking about the GPUOpen Hybrid Reflections sample and how it relates to Far Cry 6. So as Stephanie mentioned, Far Cry 6 shoots an SSLR ray, and if there's low confidence, it shoots out a DXR ray. The only exception to this is reflective pixels that are near the camera, which always shoot a DXR ray and never shoot a SSLR ray, which saves a little bit of time. The hybrid sample reflections is similar, where we also shoot SSLR rays, and if we are low confidence, we shoot a DXR ray. But we have feedback counters that we reproject frame to frame. And what they do is they try to remember what pixels shot what type of rays. Were they hybrid, were they DXR only, were they SSLR only? And what we try to do is we try to avoid shooting out SSLR rays for pixels that previously required a DXR ray to find an intersection. And so instead of just having that benefit for pixels that are near the camera, we get that benefit for any surface that happens to satisfy that heuristic, regardless of its distance from the camera. So you can definitely think of this as an iteration on top of the hybrid reflections in Far Cry 6. So how is this actually implemented? The feedback counters are stored for every 8x8 tile of pixels. And you can see the format there in the slides. They are a single U32 with 2 frames of statistics, each frame having hit and miss counters for that tile. There's a couple of issues that we need to fix with these tiles when we're implementing them, or mainly to say that we had to work around, and that is that when you have motion vectors for your tile, you have a lot of different motion vectors for all the different pixels. So you need a workaround here to actually reproject the tile. And the workaround we chose is that we choose a random pixel and we treat its motion vectors as the motion vectors for the whole tile. What you'll also notice is that we've only ever mentioned ways of switching SSLR to DXR. We need a mechanism also to switch from DXR pixels to SSLR, because otherwise our feedback counters over time will only ever converge on having DXR rays, and we'll never get the advantage of using SSLR for the rays that don't need DXR. And so the way this is actually done is randomly pixels that are DXR only will sometimes become hybrid. And then what we'll do is we'll confirm whether or not we need the DXR ray to find an intersection, or if an SSLR ray is high confidence enough to skip the DXR traversal completely. So here's the full workflow for this technique. We first reproject the previous feedback counters using motion vectors. We roll our dice to turn pixels randomly that were previously DXR into hybrid. The hybrid rays go through screen space SSLR, and if they get an intersection, then we increment our hit counters. But if they don't, then we increment our miss counter, and then we combine them with our DXR rays that we previously separated, and we go through the DXR pipeline to find our intersections. Our hit and miss counters get combined, and then we reproject, and then we repeat the same thing for the next frame. So in conclusion, Hybrid Raytraced Reflections is a very powerful technique that gives a good quality boost over SSLR. There's a lot gained by having more visible than just screen space information in your reflections. Keeping Raytraced Reflections hybrid makes this technique a lot more viable for real-time performance. A lot of performance is saved by using SSLR arrays where applicable. You do want to plan ahead for your asset system integration and handling of materials, because this will be something that needs to be adjusted or integrated into your ray tracing shaders. And it's important to keep in mind how ray tracing runs on the hardware and its performance characteristics. So we went over the shader tables and their sizes, as well as the different forms of divergence, and you want to keep those things in mind when you're designing your ray tracing pipeline, so that you can use as much of the hardware's performance as possible. And for the AMD's Hybrid Reflection sample, it's currently available on the provided GPUOpen link. It's a DX12 implementation with docs, and the source code is public and available under an MIT license for you to experiment with today. Thanks for listening to our presentation, and welcoming Q&A.